Okay, so let us now do an example, and so that means we are going to look at a heuristic to find the independent set, actually the maximal independent set, and then see how to determine the other two. Okay. Alright, so we'll call this heuristic as a minimum neighbors heuristic. So remember, the traveling salesman I called as a nearest neighbor heuristic, so that's different from this. So this is called the minimum neighbors heuristic to find the maximal independent set. Now again, as I said, you want to find the maximum independent set. So you, given a set of vertices in the graph, you want to include as many vertices from this set in the set of maximal independent set. Okay, so we want to maximize the size of the independent set. Okay, so that's objective, remember. So we are going to again look at a greedy strategy here. Now again, from the definition of an independent set, there should not be an edge between any two vertices that we end up as independent set, right? So which means what? If I include a vertex in the independent set, its neighbors cannot be included in the independent set, right? So for example, if I include V2 in the independent set, I cannot include V1, V3 or V5 also in the independent set, because if I include say V1, then you're going to have an edge between two vertices in the independent set. That violates the definition. So if I include a vertex in the independent set, its neighbors are automatically going to get excluded or ruled out from being part of the independent set. So this is the observation we are going to make use of the strategy for this as a greedy strategy for the heuristic. So given these 6 vertices, we can think about which vertex should be kind of included or preferred for inclusion in this independent set, the maximal independent set. So if you look at say the degree, which is the number of neighbors of a vertex, so for V1 it is 3 neighbors, V2 it is 3 neighbors, V5 it is 5 neighbors because it has an edge to all the other 5 vertices, V6 has 2 neighbors and so on. So you think about it, if I include V5 to be in the maximal independent set as a first vertex to be included in the maximal independent set, the rest of the vertices are automatically getting ruled out. I cannot include any other vertex in the maximal independent set, right? So that gives us the idea. So we should not prefer a vertex with more neighbors. On the other hand, if I include a vertex with fewer neighbors to be part of my maximal independent set, say V4 or V6, so include V4, then including V4 will exclude only 2 of its neighbors because it has only 2 neighbors. So because of including V4, only V1 and V5 are going to get excluded from being considered to be part of the maximal independent set. The other vertices are still candidates for being considered to be part of the maximal independent set. So that is the strategy we are going to use here. We are going to prefer nodes with minimum neighbors for inclusion in the maximal independent set. And we are going to build this maximal independent set in a sequence of iterations. So in each iteration, we are going to add one vertex to the maximal independent set and then move on. So to begin with, we are going to find the neighbors for each vertex, like I show here, and we are going to prefer a vertex with a minimum number of neighbors for inclusion in the maximal independent set. So we'll start with either V4 or V6. We have a tie. So we break the tie with the lower ID. You could choose in any order, doesn't matter. So we'll use the lower ID as a tie. So we include V4 as the first vertex to be part of the independent set. So that will exclude V1 and V5. So I color them. So we can say V1 and V5 are kind of covered by V4. Covered means they are a neighbor of at least one vertex in the maximal independent set. So that means we have to recalculate the number of uncovered neighbors for each vertex. So to begin with, we can say we actually determine the number of uncovered neighbors. But since no vertex is covered, every vertex is uncovered to begin with, we just say the number of neighbors. But actually what we are trying to use is prefer nodes that have the minimum number of uncovered neighbors. So at the end of the first iteration, this is what we are going to have. So we redetermine the number of uncovered neighbors for each of those remaining vertices. So for V2, it initially had 3 neighbors uncovered. Now it is going to have only one neighbor, which is V3, that is yet to be covered. So V2 has one uncovered neighbor. V6 also has one uncovered neighbor. Now V3 has two uncovered neighbors, V2 and V6. So now this for second iteration, we prefer a vertex among these three vertices that has the fewer number of uncovered neighbors, which is 1, and which could be either V2 or V6. So we break the tie in favor of the lower ID, so we prefer V2, include V2. So V2 is now part of the maximal independent set. So V2 will cover V3, right? So that means V6 is left alone to cover itself. So V6 has 0 uncovered neighbors, but it is yet to be covered. So it will cover itself by becoming part of the independent set. So after including V6, all vertices in the graph are covered. So V2, V4, V6 will form the maximal independent set. Again, this is a heuristic. It's not guaranteed. And it's greedy strategy based also. So it's not guaranteed that for any given graph it's going to find you the maximal independent set. Now for this graph, there cannot be a maximal independent set of size 4 or more. So 3 is the maximum size of an independent set we can get in this given graph. So for this given graph, yes, this heuristic has found you the optimal solution. But again, as I said, it's not guaranteed for any graph. Okay, so that's why it is not deterministic. So the heuristic is not a deterministic algorithm. That's how you can differentiate between heuristic and an algorithm. Okay, so and it's not guaranteed to give you the optimal solution all the time for a particular problem. So once you find the maximal independent set, all you can do is take the complement of that. So complement of V2, V4, V6 is going to be V1, V3, V5, and we can say the complement of maximal independent set is the minimum vertex cover, and that's the vertex cover for this graph. And you can cross check for every edge, at least one of the two end vertices will be in the vertex cover. Okay, so let me check the time and right. So we'll continue and finish off this problem and see the second one next class. Okay, so let us see now how to determine a clique. Again, we were focused on a maximum clique, right? So this is a given graph. Now what we'll do is build the complement graph of this given graph. Now a complement graph of a given graph is nothing but you have the same set of vertices V1 through V6, but for the edges, if there's an edge between two vertices in the given graph, then the two vertices will not have an edge in the complement graph and vice versa. So between V1, V4 we have an edge in the given graph, so they don't have an edge in the complement graph. V1, say V3 don't have an edge in the given graph, so V1, V3 have an edge in the complement graph. So that's how we build a complement graph. So for any two vertices, check if there's an edge between them in the given graph. If they have an edge, they don't have an edge in the complement graph. If they don't have an edge in the given graph, then they have an edge in the complement graph. And you can lay out the complement graph in such a way that's more easy to visualize. You can draw it in any other fashion also, but make sure it satisfies the definition of a complement graph, as I just said. So once you have a complement graph, run the same minimum neighbors heuristic on the complement graph and try to determine a maximal independent set on the complement graph. And that's what we're going to do here. So for that we need to determine the number of neighbors, which is the number of uncovered neighbors to begin with. So for V1 it has 2 neighbors, V2 has 2 neighbors, V4 has 3 neighbors, again in the complement graph. V5 has no neighbors, so it is 0 neighbors, and so on. So again, for a maximal independent set, we will prefer to include vertices with fewer uncovered neighbors. So to begin with, V5 has 0 uncovered neighbors. So let's go ahead and include V5 in the maximal independent set, and V5 will not cover anyone else. So that means the number of uncovered neighbors for the other vertices is going to remain the same, right? So we'll make use of the same numbers that we have found here. So we see 2 as the next smallest value for the minimum number of uncovered neighbors that we have found. So again, we have a tie, we can pick the lower ID, so we'll pick V1 as the vertex to be included in the maximal independent set. So far we have included V5 and V1, and V1 will cover 2 of its neighbors, so V6 and V3 are covered. So the candidates are just V2 and V4, and they are kind of covering each other. So V2 has V4 as uncovered neighbor and vice versa. So the third iteration will pick one of these two vertices, so we can pick V2 as to be part of the maximum independent set, and that will cover V4. So V1, V2, V5 will form a maximal independent set in the complement graph, and you can cross check. There's no edge between any two vertices in this complement graph. V1, V2, V2, V5, V1, V5. There's no edge between any two of them. Now we can claim the maximal independent set in the complement graph is a maximum clique in the original graph. Now why is that? Remember the way we built the complement graph, if there is no edge between the vertices, there's an edge between them in the complement graph. If there's edge between the vertices in the given graph, there's no edge between them in the complement graph. So if V1, V2, V5 is the largest subset of vertices that don't have an edge between them in the complement graph, that is also the largest subset of vertices that have an edge between them in the given graph. Automatically, by the way we build the complement graph, this can be satisfied, right? So we can claim the same set of vertices V1, V2, V5 is the maximum clique in the complement graph, in the given graph. So again, let me repeat. Once you find the maximal independent set in the complement graph by running the minimum neighbors heuristic, we can claim the same set of vertices is the maximum clique in the given graph, because by definition of maximum independent set, there is no edge between any two vertices in this set. So V1, V2, V5, there is no edge between any two of them. And that's a maximal subset of vertices that you can find with no edges between them in the complement graph. That means that is also the maximal set of vertices you can have in the original graph that have an edge between them, because the way you build the complement graph, if there's no edge between V1, V2 in the complement graph, there's an edge between them in the given graph. Similarly for the other combinations. So that is also the largest subset of vertices that have an edge between any two vertices in the set and located in the given graph. Okay. So what we saw is, using one single heuristic, we are able to find all the three: independent set, vertex cover, and the clique. Of course, maximum independent set, minimum vertex cover, and the maximum clique. And you see the polynomial reduction. In one case, it is just taking the complement. The other case is building the complement graph. And we saw from the traveling salesman Hamilton circuit problem, given a graph, building a complement graph can be done in v squared times. It's also a polynomial. So that's why we say all these polynomial reduction is really having a polynomial time. So if you determine one of them, you can determine the other. Okay. So we'll stop with this. We have one more example and one more thing to see, which is connected dominating set. So connected dominating set will be the last topic we're going to see in this module, and with that we'll finish the syllabus.